Hi, Girl Scouts! Welcome to another activity on your journey to complete the Get to Know Nuclear Patch. My name is Ashley McKendry. I'm an engineer in the energy industry, and I'll be your guide throughout this video. Many of you already know that radiation is an important part of nuclear science, but this video will teach you more about radiation in our environment and how we measure it. Let's go ahead and get started. So everything around us is made up of atoms. Everything from the screen you're watching this video on to maybe the sandwich that you had for lunch, all made up of atoms. Atoms are one of the smallest particles in existence, and they're so small we can't see them with the human eye, and we can't even see them under a microscope. The example you're looking at here is the uranium atom. This atom, like all the others, is made up of tiny elements with different charges. The center of the atom is called the nucleus. It's made up of a concentration of neutrons and positively charged protons. Uranium, for example, as shown in this picture, has 92 protons and either 143 or 146 neutrons, depending on the isotope. The other component of the atom are the negatively charged electrons. These float and circle around the nucleus and make up the rest of the atom. So what might make an atom radioactive? Do you have any idea? An atom becomes radioactive when it has extra protons or neutrons in the nucleus. This makes the atom unstable and unbalanced, and causes the atom to release energy and eventually become a different atom. The energy that the radioactive atom releases is called radiation. Radiation comes from many sources around us. It comes from the atoms in the earth, through radon, a type of radioactive gas found in soil. It can come from potassium found in our food and drinks, and it can even come from the sun, as many of you probably already know. The energy released through radiation can be really useful. It's important to many technologies that we use daily. Nuclear power plants, it's used to generate heat that's used to generate electricity. So radiation is a really important part of the world around us and physics. There are four major types of radiation. There's alpha, beta, neutrons, and gamma rays, which are a type of electromagnetic waves. These types differ in how heavy they are, how much energy they carry, and also how far they can travel through different objects. Alpha particles are the heaviest type of particle radiation, and they are made up of 2 protons and 2 neutrons. Beta particles come next. They are made of electrons, and they have a small mass and are negatively charged. Gamma rays are the third type of radiation, and as I mentioned, they're a type of electromagnetic wave, which means you've probably experienced them when you're getting x-rays at the dentist. The last type of radiation is called neutron particles. So low levels of radiation are around us every day. Like I mentioned before, some dosages of radiation come from natural sources like the sun, rocks, or other sources. May come from household items like granite countertops or smoke detectors. We also know that too much radiation can be harmful, and that's why the dentist has you wear heavy lead jackets when you're getting your x-rays. And that might make you wonder, well, how are nuclear power plant staff protected from radiation? The first way is through physical shielding. Physical shielding protects workers and the environment from high dosages of radiation. Different types of material can be used for shielding, anything from paper to concrete, but it depends on the type of radiation that needs to be shielded against. So for example, alpha particles cannot penetrate your skin, and they can be shielded by something as thin as paper or clothing. Beta particles can penetrate the skin, and they're shielded by clothing, but they're best shielded by thin layers of light metal, so something like aluminum foil. Gamma rays can pass through the human body. They are shielded by dense materials like lead or concrete. And the last type of radiation is neutrons, which are strong. They can penetrate through the human body, and they're best shielded by materials that contain hydrogen atoms like concrete or water. So radiation can be measured and detected. And so the second way of protecting workers at nuclear power plants comes from small monitors that workers wear pinned to their shirts. These monitors look something like image number 1 on the screen, and they're even smaller than a cell phone. They're used to track how much radiation a worker might be absorbing while they're at work. And radiation is measured in units called millirem. So this is the unit you'll see being recorded on these types of devices, and that's what is tracked as workers monitor their dosages for safety reasons. For other uses like science fields and at universities where they might be doing research on different materials and different radioactive components, they might use something that looks similar to image number 2. These are called Geiger counters. They're named after Hans Geiger, who is one of the scientists who worked to develop radiation measurement tools in the early 1900s. So later on, we're actually going to get to use these types of measurement tools and really see how they work. There are many different types. Today, what we'll be looking at later is similar to image number 2 and image number 1. However, there are several different types, such as the version in figure 3, which has a really large circular detection area that's better for measuring alpha and beta particles. And it's a fun fact in the industry that they actually call this the pancake detector because of its shape. So now that we've discussed radiation, how it's measured, how we can be protected from it, let's talk a little bit more about how it exists in our environment. So here's a statement. What do you know that we get most of our radiation dose from nuclear power plants? If you're completing this activity with a partner or a parent or guardian, feel free to pause the video and discuss. So this is a myth. Humans absorb radiation from many sources every day, but living near a nuclear plant does not increase your exposure to radiation. Like I mentioned before, nuclear power plants are designed to protect citizens from radiation using shielding. Large concrete walls in buildings called containment protect the environment and workers from radiation that's generated while creating electricity. So that might make you wonder, where do we get our dosage of radiation from? The United States is currently the largest consumer of energy created by nuclear power, but the majority of the radiations that Americans absorb comes from the world around us. You'll see in this chart that many adults absorb most of their radiation through medical procedures, so getting x-rays or different types of scans. A very small percentage of the radiation we absorb comes from places like outer space, maybe from the sun, or products we use like smoke detectors and other industry and occupational exposure. But another big portion of this, like I mentioned before, is just coming from the earth. So it's naturally found in the soil and other things outside in nature. So now that we've talked a little bit about where we might get our radiation doses, let's go and try to learn a little bit more about Geiger counters and how radiation is measured.
Welcome to part 2 of the radiation and detection segment of your Get to Know Nuclear Patch. It's Ashley McKendry again, and I'm going to be going through a demonstration today of using 2 different Geiger counters to test 2 different household items that have very, very low levels of radiation, but we can actually still detect with the Geiger counters. So today we're going to be measuring from an old plate that has an orange glaze, and then we'll be detecting from a smoke detector that I've actually taken apart for the purpose of today's video. So we'll get to see which of these 2 emits the most radiation, and then we'll get to go through an example of how shielding works to limit the radiation coming from an object. So why don't we first start out using the smoke detector. And today I have 2 different Geiger counters. I have this larger model that's a little bit older, and then I have what I would almost call a pocket Geiger counter that engineers or radiation workers might be able to take with them on the job, take wherever they're going. Today I'll do one example showing you guys how the yellow Geiger counter works, but for the most part I'm going to work with the newer model just because its audio is better. The old model has its audio through a headset, which will be a little bit difficult for you guys to hear on the video, and I think that's the cool part. So we'll go ahead and get started. The first thing I'm going to measure, I'm going to move the plate out of the way for now. The first thing I want to measure is the smoke detectors. So here's my Geiger counter. You can see there are there's the on and off switch, and then there are a couple different settings. For the purpose of reading the smoke detector, it has such low levels of radiation that I'm going to use the lowest setting. That way hopefully we'll be able to catch it. It is so low that it's hard to read, but we'll do our best to see how it works. So I'll go ahead and put this down. What I want to talk about before I do the reading is actually what is it about a smoke detector that makes it slightly radioactive. And it's actually the americium-241. It's an element, an isotope, sorry, that is used in the smoke detectors. It actually has its own electrical field, and an electrical current, and the smoke particles actually disrupt this electrical current, and that's what causes the alarm to sound. So the way smoke detectors are built, they have their cover, but when you take that off, you can actually see inside. And some of them, not all, have this little casing where they store the radioactive material. So hopefully I can bring this closer to the video and you guys can see right here, there's a little radioactive symbol, so you can see what it's got in there, and you can actually see, it's hard to tell, but you can actually see it does say AM 241, which is their americium 241. So that's exactly what's in here. So I'll go ahead and turn on our Geiger counter and we'll see if we can get a good reading. So you guys can hear it chirping, and that's it catching some of the radiation. So it's really, really low. You can see it's barely moving our cursor, and kind of comes and goes because of how weak it is. But I would say that this smoke detector emits about 0.02 millirems per hour. So very low dosage compared to what we discussed earlier, that your average American gets 620 millirem per year from the earth around them and medical procedures for the most part. So that's our first example. So you can see pretty low levels of radiation. Our second example is the orange plate, which is a little bit more exciting because it does have quite a bit more radioactive material in it. So these older plates, it's not something you'll see a lot of today, but the type of glaze that is used is actually known for its radioactivity because of its uranium oxide that's used in the glaze. So it's perfectly safe for eating because, like I said, it's very, very low levels, but it does have enough to be read on the Geiger counter, and it's pretty interesting. So I'll go ahead, and I'm actually going to use both systems for this example so you guys can see how the yellow one works too. So the yellow one has a dial just like the Pocket, and you can turn it on to whatever setting you think is appropriate, and you can test it for whatever material you're using. And then what I'll do is I'll go ahead and put the material that I want to test by these sensor openings in the probe that does the radiation sensing. So when I put the plate here, you guys can hear, and this one's loud enough that you should be able to hear, hopefully through the speaker, but if not, hopefully you guys can see when I turn the dial up a little bit that the plate gets to about 0.1 millirem per hour, and that's with the yellow tool. And so just in case you guys couldn't quite hear that, I'll turn off the yellow Geiger counter and push it aside, because now we're going to use the Pocket tool, and we'll actually use the book in a few minutes to show you guys an example of how shielding works. So like I did before, I turn on my Geiger counter by switching the dial over, and I switch it all the way over to audio, that way we can hear it. And so you guys will see that the plate kind of makes it go crazy. There's quite a bit coming off. So when I move this dial up to a different sensor, you can get a better reading, and we can see that just like the yellow, we stop at about 0.1 millirem per hour. So the example that I want to show you guys is actually what happens when we use a book to shield the plate. So if I put my Geiger counter down and I put my plate, we'll actually be able to hear the radiation again through the Geiger counter. But if I line up a book in between the plate and the Geiger counter, you can hear that the sound's no longer there, and you can see, hopefully, that my reading is at 0. And that's because, like we discussed in the learning segment before this demonstration video, that paper can be a great shield against certain types of radiation. So this is just demonstrating that concept. All right, well, I hope you guys have learned a lot through this video, got the opportunity to see 2 different types of Geiger counters, and learn a little bit more about some of the occupational radiation that might come from some of the products that you use.